Good morning, everyone. So, can you please confirm whether you are able to hear me and see my screen clearly?
Yes, sir.
Okay, fine. So, in the previous class, we were talking about various types of ways in which the welded connections can be provided. So, there was groove weld and there was fillet weld, and then we were talking about what are the different types of terminology that are associated, which symbols are used in the drawing, in the structural and fabrication drawings to show these connections, right? To show the different types of welds. And there are various small details that you should be familiar with, because when you read a drawing, from these kind of details, you have to figure out what are the dimensions of the weld and how to calculate the strength of that kind of a weld. We were talking about also the advantages of welding, and I think this is where we had stopped last time. So I'll just quickly repeat a few things here. So welded connections are very good in a few aspects. The one very important one is that the welded connections are relatively stiffer than bolted connections, right? Another one is that welded connections, especially if you go for a fillet weld rather than a groove weld. Groove weld, again, you require very high level of precision in your fabrication. But if you are going for a fillet weld, usually the fillet weld is more forgiving. So even if you have a relatively less level of the fit, right? The fillet weld can accommodate all those kind of issues, minor issues, and it is usually and that's why fillet weld is typically more commonly used than groove welds. Okay. Um, Welds can be used in more versatile geometries. Okay, and I had given an example in the previous class. Let's say you want to connect two tubular members at a particular angle, right? So in that kind of a case, the geometry of that intersection of the two tubes will be quite complex, and providing a welded connection, providing a bolted connection for that geometry is very complex, will be very extremely time consuming and labor intensive, and you will require very high level of skill set also. Instead of that, welded connections are very easy, and even that requires decent amount of machining and decent amount of skill set, but still it is much easier than bolted connections. Welded connections also provide airtight connections. So wherever you need airtight connections, you can go for welded connections. Okay. And most important one is that the welded connections, because you don't have to drill any holes, so the cross section size does not reduce, unlike bolted connections. Because in bolted connections, you have to drill holes. Bolted or riveted connections, the holes have to be present, and the holes sometimes eat up a large portion of the cross section area. So as a result, your net cross section available to you for resisting the forces is reduced in bolted and riveted connections, whereas in welded connections, that is not a problem. So your strength, member strength, is relatively higher. Okay. There are some, of course, disadvantages also. So in comparison to bolted connections, so for bolted connections, you have to drill holes, and those holes usually have to be drilled with a very high level of accuracy. So there you require certain level of skill set. But most of the drilling of the holes is done in the shop, so that is okay. But most of the bolting work, that is tightening of the bolts, is done on the site, can be done by relatively less skilled workforce. Whereas welding is a very highly skilled work, and so therefore the labor cost and the availability of such kind of workers who can do a proper structural weld, such kind of workers are very expensive, and also their certifications and all those things are very expensive. Okay, and availability of such workers is very low. So in India, I do not know how strong the certification program is, but in the Western world, the certification for good quality structural welds is very expensive, and it's very time consuming. They have to work for years and years to get that kind of a certificate, because you have to be consistent. If you have to provide a weld of a particular size, say fillet weld, right? So if you stay for too long, you can at one place, let's say you are moving with the electrode, right, along the length of the weld. So you have to maintain that constant speed and make sure that you are covering the entire surface and you are depositing the same amount of filler material throughout, right? So that requires a very high level of skill set, plus controlling the current and voltage and all those things for the requirement of the job, and requirement of what size electrode you are taking. So there is quite a bit of science involved in that as well. Welded connections usually have this issue of failure under fatigue loading, and the reason for that is that when you there are two materials that you are mixing. One is base metal, and the other one is the filler metal. And first, one issue is that the filler metal usually has relatively low level of ductility in comparison to the base metal. Plus, another thing that you are doing is you are heating it and melting it, right? So after you melting it, there was certain ductility in the base metal that was achieved by doing a lot of during the rolling process, because when the rolling was done, the material was deformed several times and slowly cooled down. As a result, you increase the ductility of that metal. But now during the welding process, the temperature control, or in the cooling phase, after the material has been deposited, the temperature control is not very good. It is simply exposed to ambient temperatures, and it cools down at different rates at different places. Sometimes it can cool down relatively faster, and as a result, you lose some of that ductility. Plus, the filler material that you are using also may not have the same level of ductility as the base metal. Also, during the process, as we had discussed in the beginning, there are some impurities that tend to deposit on the surface, and some of those impurities, or some of those impurities may actually penetrate the weld and may be present inside the weld. So if there is any impurity present inside the weld, or if there is a crack inside the weld, or if there is a lack of fusion of the two metals, if the two metals don't fuse perfectly, and there are minor cracks available, wherein there are basically, you can imagine that these are basically the faucets kind of surfaces which are forming between the two metals, where they have not fused properly. So those will be the points where the cracks will initiate very early, and that leads to a poor performance under fatigue loading in welded connections. Whereas the bolted connections and other types of connections, or metal in general, may have a much better performance against fatigue or against very large deformations, whereas welded connections typically perform poorly. Different grades of filler materials are available, so that we will talk about that in a minute. So different grades of filler materials are also available, but usually the one that we go with does not have a very high level of ductility. So therefore, wherever you have a requirement of a high level of ductility, or you have to operate under very low temperatures, or you are expecting impact loading, in such cases it is better to go for higher grade filler material. When I say higher grade, it is from ductility point of view, higher grade. Okay. Welding is very difficult in inclined positions, vertical positions, overhead positions, and obviously you know that because the metal is molten for a while, right? And it needs some time to solidify, to harden. And so therefore, if I have to do welding in upside down position, right, it is very, very difficult. But bolting is not that difficult. I can do bolting still in an upside down position, but welding is not possible in that kind of a situation. So special arrangements have to be made, or otherwise usually what you have to do is you have to find a way to reach up the above side, and from there you have to do the welding, and sometimes that leads to difficulties in welding process. For groove welds, you have to do the edge preparation, which you can compare with the drilling of the holes in bolting. So there may be extra cost involved, extra machining involved if you are going for a groove weld, but if you're going for a fillet weld, that's not a disadvantage, that's not a problem. You don't have to do much edge preparation. Okay. Another major issue with welded connections are the distortions, or development of residual stresses. Okay. And we had discussed, I'm sure it must have been discussed in the chapter on columns also, because you may have beams which are hot rolled beams, or columns which are hot rolled columns, and you may have beams or columns which are built up sections. When the sections are built up, often they are welded together, right? So when you weld them together, you introduce a lot of residual stresses, and the concept is same. The residual stresses arise in welded connections just in the same way that they arise in the hot rolled sections. However, these residual stresses in welded connections are much more concentrated and can lead to distortions. So if you are going for a symmetric type of a welded section, welded built up section, then the distortions will not be visible, but they will be blocked, they will be locked inside the member as residual stresses. One example can be given to you wherein the residual stresses will lead to deformations. So in this particular case, what you can see here is there is a plate which has this width and this much of length. Okay, so these are the two views of the same plate, and we are not connecting another member to it. All we are doing is we are drawing a line with the weld material along the length. So this is the cross section of that plate. Along the length, a weld material is deposited. So basically, we just took an electrode and we just went from one end to another with that through the welding. So we just kept depositing that welding material, molten welding material from one end to other end. And at the end of the process, once the material cools down, you will see that the plate will bend like this. Even though the plate was straight to start with, it would bend like this. And obviously, why would it bend? Because that filler material that I have deposited, originally it had the same length as the metal, the base metal, but then when it started to cool down, it started to shrink and it had already fused with the base metal. And when it shrank, it caused the deformations in the plate. And you can imagine if you're going for a very complex geometry, like if you are going for a stiffened plate or something like that, where you have a plate and you have a number of stiffeners running in both directions or more than two directions, maybe in various directions. And if you are having to weld all of them, these will lead to large distortions in the plate. Okay, and there are specialized people who can anticipate, who have enough experience to figure out how, in which order they should do the welding. And there are some guidelines, but in addition to that, you also need experience to figure out in which order you should do welding in various situations, so that you can minimize these distortions. Otherwise, these distortions can be so bad that by the time you are done with your almost all welding, by the time you reach the last parts to be welded, they will not fit at all. The components will be so badly distorted that the last components, the last parts will not fit. Okay. So this is something that one must be very careful about. That is usually not a problem with bolted connections. Okay. Any questions so far? I can see that attendance has dropped again. Today again only 8 people have joined. Yeah. All right. So in order to control the distortion, there are various ways. One way is to so for example, there are certain guidelines. These are available in the Indian code also. So do not overweld. What does it mean? Do not overweld, the first one. So for example, let's say you require a certain size weld. You require a fillet weld of, let's say, leg size of 8 mm or 7 mm or 6 mm. Whatever you require, you provide only that much. Do not go overboard. So if you require 8 mm, don't go 10 mm unnecessarily, unless there is a reason for that. Yeah. So because if you go extra, if you provide extra welding material, that means you are introducing extra distortions. So that is one way, which is kind of obvious. And also another one is try to go for as few passes as possible. So for example, let's say you want to do an 8 millimeter fillet weld. Maybe I can draw it here. Let's say I want to go for an 8 millimeter fillet weld. So this dimension is 8 millimeter. So that's how you define the size of the fillet weld. So this is the size of the fillet weld. And what I find out is that with a single pass of my electrode, and that electrode size also depends on the fillets, the size of the weld and the base metal and all that. So, or the machine capacity and all that. So let's say with a single pass, I can make a certain size weld. So what I'm planning, let's say, is to do this. One pass will be this. Then I will come back again. I will do this pass. Then I will come back again. I'll do 3 passes like this. Okay, with 3 passes I'll make it, and then I will machine it slightly to make it smooth. Let's say that is the plan. Alternatively, I have another plan wherein I can make it in 4 passes, and both of them are equally feasible for me. I can do this, and then I can do this and this and this. Let's say I can do the same weld in 4 passes. Now it is better to go for as few passes as possible, or in other words, use the thickest possible electrode for that weld size. Right? So for 8 mm size, of course, if you need an 8 mm size weld, you cannot use a 14 mm electrode. That will not be a very good idea, because then you will not have a very good control over the size of the weld. Okay, so you should use the electrode of appropriate size and try to minimize the number of passes that you have to use. Okay, so this option is, if both these options are available to you, this option is better, and this second option is not good. Okay, if both of them are available to you. use intermittent welds. That is a very important one, and that is one thing that you can immediately know whether a person knows his welding or not. Is, for example, if these are the two plates that you are welding. These are the two plates. One plate is perpendicular to other. Maybe I can show you the other view. So this is the top view. Side view will be, let's say this. So let's say I have these two plates that I need to weld, and I need to provide fillet weld on both sides throughout. Okay. So the requirement is that there should be a fillet weld on both sides of this plate throughout the length. Now, it's not a good idea to go straight forward from one end to other. So it's not a good idea to do the, this is the top view. It's not a good idea to, see if I can put the color, to do this weld first and then do this weld. This is not a good idea. This is not a good option. Alternatively, what you should do is one of the two. You should either do it like this. So 1, 2, you can see 1, 2, 3, 4 here, right? You should go 1, 2, 3, 4, 5, 6, and then come back again and do 7, 8, 9, 10 to fill those spaces. Okay. The idea is that you should go in small segments rather than going a long length with a single pass. Okay. You should go in small segments. So the idea is that these free spaces that you leave there, they will accommodate some deformations. Otherwise, what will happen is that when you are going from one end to the other straight away, without welding the other side at the same time, and also without ending the other ends of this plate at the same time, all these deformations will keep accumulating. By the time you reach the other end, it will be badly distorted. Alternatively, you can also, instead of going for 1, 2, 3, 4 like this, you can also go 1, 2 in a staggered way. 1, 2, 3, 4. This is even better. 1, 2, 3, 4, 5, and then come back again 6, 7, 8, 9, 10. Okay. So by using this approach, you can stagger the stresses, and then you also give them a way to release the to accommodate the deformations. Okay. All right. So now the basic understanding of welded connections, how they behave, I think I have covered in enough detail. If you have any questions, you can ask now. Now we will move into the designing side of it. No questions? Fine. So when it comes to designing of the welded connections, by designing I mean calculating the strength of a welded connection, right? So there are two types of connection welds: groove weld and fillet welds. And first we have to see how to provide the dimension, how to specify the dimensions of these welds. So if there is a groove weld, the first examples are that of the groove welds. So these both of them are groove welds. So in this particular case, two plates of different thicknesses, T1 and T2, are welded together with a groove weld. Okay, and obviously, when one plate is thinner than the other plate, the groove weld will be assumed to be the size of the thinner plate. Okay, in this particular case, both plates are of the same size, and the full penetration groove weld is provided. So the size of the groove weld is taken same as the thickness of the plate. Okay, that is obvious, right? And as I had explained before, since there is no geometric complications with respect to groove welds, so you can assume that the stresses are flowing straight away as they were flowing in the base metal. You can assume that the base metals have been fused together in case of a groove weld. So the calculations are much more straightforward. In case of a fillet weld, however, the calculations are relatively more complex. So a fillet weld is triangular in shape like this, right? So you would typically have, if I may draw it, you would typically have a plate sitting, let me choose a different color. You would probably have a plate sitting here, and then maybe a plate sitting here. The geometric properties could be anything. And then between these two plates, you will provide this in this at this um, common surface, you will provide the fillet weld, right? So now what may happen is that maybe this plate is being pulled outside the board. Maybe you can think that this plate is being pulled and this plate is being pushed. Okay, there may be this situation. So there can be one force condition like this, right? So in that particular case, there will be the fillet weld will be purely in shear. You understand that, right? So this plate is being pulled and the lower plate is being pushed. Okay, and the fillet that is connecting the two plates will be purely in shear, and it has to transfer all that force between the two plates. Alternatively, you may have a situation wherein this plate is being pulled this way and this plate is being pulled this way, right? That is also one possibility, correct? So if that is the situation, so you have two plates like these, or you may have, instead of, it may be more easy to understand if I change the geometry of this plate. Sorry, it isn't as easy to draw on this thing. Let's say this is another plate and then it is being pulled this way. Now it is obvious, right? So you may have two plates with a lap connection and then they are being pulled in different directions. So in this kind of a situation, the fillet weld will not be under pure shear. It will be a combination of shear and tension. Okay, so either way, just keep in mind that these two stress states exist for a fillet weld. And what the code says is that the fillet for a fillet weld, if it is of equal sides A and A, so the size of the weld is A. So weld will be called of size A. However, the effective width or effective thickness of the weld is given by this smallest dimension. Okay, because for this fillet weld to fail, it can fail at this surface, which is the smallest dimension. It does not have to fail here, right? So therefore, this TE, that is 0.7 times or 0.71 times the weld size, is the effective thickness of the weld. However, if the weld is not of equal sizes, which is relatively uncommon, but it may happen. So if the weld is designed in such a way so that A and B are not of equal size, in that case, the effective thickness of the weld will be again the smallest surface, the smallest distance, but that will have to be calculated using this expression, which you can derive from direct geometry. I don't have to go into this detail, right? So this part is obvious. So this is how you calculate the effective thickness. So basically, when it comes to the failure of a groove weld, you talk about this surface failing. When it comes, or this surface failing, right? Because both of them are T1 or TE. TE is equal to T1. When it comes to fillet weld failing, you talk about this surface failing, because this is where the stresses will be highest. This surface is failing. Okay. Now, before we get into the behavior of groove welds, I wanted to quickly talk about the behavior of welds, fillet welds. Okay, so I had mentioned about two possibilities, right? One possibility in the previous example was the case where you had one plate and you had another plate, and there is a fillet weld, and the plates are loaded in such a way so that one plate is being pulled and the other plate is being pushed. You are familiar with these symbols, right? So when you have a circle and a dot, that means you are pulling it. The arrow is pointing outward. And when you have a circle and a square, that means the arrow is pointing into the screen. Okay, so you are pushing it. So when you have this kind of a loading situation, your fillet weld is under pure shear. Okay, that weld is also known as side weld. If you imagine, let's say you have this kind of a configuration where you have one plate and you have another plate welded to it, and this theta angle is varying. Now if the theta angle varies and becomes equal to 90 degrees, that means you're talking about a weld on these surfaces on the sides. So that's why it is known as side weld. This is the same situation, side weld. Okay, so you can imagine that you are talking about, if I may just extend the bottom plate a little. Okay, sorry. So this may be pulled out and this is being pulled out, pushed in. So the bottom plate is being pushed in and the top plate is being pulled outward. And then you have these two fillet welds. So this is a side weld situation. Okay. And in case of a side weld, the capacity is relatively smaller capacity of the weld, same fillet weld. So in this particular case, what is drawn here is a situation where the FU for the plate material, the base metal, is 511 MPa, and the FU, ultimate stress of the weld filler metal, is 565. Now, in the fillet weld, when you provide a weld, you don't know exactly how much of the base metal has come into it and how much of the filler metal is there, because they melt together, they fuse together, right? So we typically take the smaller of the two for further calculations. But for the time being, just you consider that they had these two individual ultimate stresses, but the fillet weld will fail at a stress level which is much lower than either of these two, which is at 300 something. Okay, and as I had mentioned, this kind of a situation is pure shear situation, right? So this is a pure shear kind of a situation. What is the problem? Pure shear side weld situation. Okay, and the capacity is very low, and you can understand that it should be governed by FU divided by root 3. So if you take FU divided by root 3, take the smaller of the two FUs and divide by root 3, you will get somewhere close to that value. Okay, because that is pure shear situation. Now if I change the type of loading I'm applying, and maybe I'll have to draw it again. So if the loading is in such a way, again drawing the top view now, this is your base bottom plate and this is your top plate, and the weld is at this edge, and I'm applying the load here, applying the load here. So for this weld, for this particular weld, now the theta would be 0, right? If you see this theta angle, that is 0, so that is end fillet, right? And if you look at this kind of a fillet in the other view, this surface is being pulled this way and this surface is being pulled this way. So it is not a pure shear situation, it is a combination of shear and tension. And from the experiments you can see that the capacity is relatively much higher. It's almost in the same ballpark as the FU weld and FU plate values, okay, in that kind of situation. So this is an end fillet, and it's a combination of shear plus tension, and the capacity is much higher. Okay, and also experimentally you can see that this kind of a fillet, even though it has higher strength, it has less ductility because it loses the strength very quickly after the peak value. So peak value is achieved much sooner and then it loses the strength much faster. However, the side fillets, they are much more ductile. They achieve maximum strength after a long deformation, and then they maintain the high value for a longer distance, for a longer deformation value. Okay, so they have higher ductility. So this is a higher ductility, this is a case of lower ductility. Okay, so we know that end fillets behave differently from the side fillets. However, some of the codes incorporate these differences and allow you to design the fillets accordingly. In the Indian code, you are required to use only FU divided by root 3 value, no matter whether the fillet is or the weld is an end fillet or the side fillet. Here for the FU, you will use the smaller of the two FU. So you have two FU plate, FU weld. You are required to use smaller of the two FUs and divided by root 3. That is assuming that it is failing in pure shear, and that is a conservative estimate. So that is fine. So the Indian code requires you to use the conservative estimate of FU. The groove weld, however, so this was the fillet weld behavior. The groove weld, whether it is in shear or whether it is in tension, you assume it to be behaving just like the base metal. So whatever you do for the base metal, you do the exact same treatment for the groove weld as well. Okay. Some information about the different types of electrodes. So electrodes are usually classified as this. Here you can see the classifications of, or the classifications of electrodes. So sorry, it's very slow. So you can see here the names are given EX40XX. So sorry, the mouse is moving very slowly. My computer has slowed down suddenly for some reason. 1 second now. Let me see again. Without the laser pointer, it is working fine, but once I switch on the laser pointer, it becomes very slow. Anyway, so you can see these nomenclatures. There is 40, then there is 41, 42, 43, and 44. Correct? And then there are some x values, EX, and then there are two x's at the end. These two x's at the end, um, they denote the characteristics such as in what position welding can be done and coating material thickness. So these are not really structural things. These are basically telling you different types of coating materials and whether what is the how fluidic this material is, so that you can do welding in various configurations. Okay, what these values are saying, 41, 42, 43, the first four represents the ultimate strength, tensile strength of the electrode filler material. So the 4 basically says if it is 4, that means it is the ultimate strength is between 410 and 540. Okay, and if it is 5 here, that means the ultimate strength is between 510 and 610. Right, so that's how these are classified. Then you have another number 0, 1, 2, 3, 4, and they basically mean 0 corresponds to, so basically these numbers correspond to a certain level of ductility. So 0 corresponds to at least minimum elongation of 16% before rupture, 1 corresponds to 20% elongation before rupture, and so on, and up to 24% you can go. Okay, also along with the ductility, they also correspond to impact strength. So basically at different levels, as you might have heard or you might have been taught about the Sharpie Vinos test, which corresponds to the toughness behavior of uh, of metals. So the 40 electrode does not have to qualify for any impact requirement. For one has to have at least this much of joules of energy consumed at 27 degrees centigrade. For two has to have 47 joules of energy consumed. If you do the Sharpie Vinos test, in that test it should consume similar energy, but even at 0 degrees centigrade. So as the temperatures are lowered, most of these metals lose their toughness, or the amount of energy they can absorb under impact loading. What the code says is that as you go higher and higher, from here you start moving downward, and as you go higher, your toughness should improve, or the toughness should remain the same, but even at a lower temperature, which is also an indication of higher toughness. So this should be these electrode materials should be having higher toughness properties. Okay, so that's how you classify the electrodes. Also different sizes and different diameters and lengths are available, and you can pick between the diameters and lengths. Now again, I don't want to go into the details of how the electrode size is decided. There are various functions that control the size of the electrode, that govern the size of the electrode. Of course, weld size is one. So if the weld size is very big, you cannot go for a very small size electrode. Also, if the weld is very small, you cannot go for a very large size electrode. So that is the direct correlation. But also there are many other factors which play a role in deciding the electrode size. Okay, and various types of electrodes and standard lengths are available in India. Moving forward to the design provisions. So if you have to design a groove weld, the designing of a groove weld is the simplest way, is the simplest thing in this provision. Basically, you assume that the base metals themselves have fused together. Okay, and the strength of the weld is minimum of the, or the smaller of the yield strength of the welding material, that is filler material, and the base material. So your Fy is basically smaller of the yield stress of weld and parent metal. Okay, and basically the strength of that groove weld, whether it is in tension or compression, for both TDW corresponds to tension as well as compressive strength, will be given by Fy LWTE. Now if you might, maybe I need to draw something to explain to you what are these dimensions. So I may have these two plates welded together. If it's a groove weld, maybe I make a V-shaped groove. Okay, and these two plates are welded together with a groove weld. Sorry, which is filled throughout. Okay, so if this is the case, the TE is, if the two plates are of equal thickness, this is TE. Otherwise, I have told you how to calculate TE. And L is the, or LW is this length. That is the length of the weld. And Fy is the yield stress. That is the minimum yield stress, minimum of the yield stress of the base plate or the parent metal, and the yield stress of the filler metal, divided by gamma mw. So in tension or in compression, this is the strength. This is the strength of this welded joint. Straightforward, right? And that is obvious because you are taking the cross section area. TE multiplied by LW is the cross section area, multiplied by the yield stress, that is the strength, total force strength, divided by gamma mw. Now gamma mw, you have to go to the table that in IS 800, the table that provides the factors of safety, resistance factors of safety for welds and bolts and bearing and all that. And gamma mw is for the welds. Now, depending on whether the weld is a shop weld or a field weld, two different gamma mw values are given. So for a shop weld, gamma mw is equal to 1.25, and for a field weld, gamma mw is given as 1.5. And the reason for that is that quality control on the field will be relatively lower quality. So as a result, you are supposed to use higher factor of safety. If the two plates are subjected to shear, that is not tension or compression as shown here, but shear force, how will that be? Shear force will be one in this direction and the other one in this direction. So if this is the kind of force that this weld is subjected to, then the strength of this weld, or the capacity of this weld will be, design capacity of this weld will be equal to this value. Okay, so that is the shear capacity. Again, Fy, but instead of Fy, we use Fy by root 3. Cross section area, that is the same cross section area that we were considering before, LWTE, and again gamma mw, which depends on whether the weld is done in the shop or it's done on the field. Okay, for a fillet weld, the capacity, as I had mentioned, no matter whether the fillet weld is an end fillet or it's a side fillet, the Indian code requires you to use Fu divided by root 3. Now you must notice that the value for a groove weld is not Fu, it is taken Fy, taken as Fy, whereas for a fillet weld it is taken as Fu. And I want you to pay some attention and think about it, and maybe in the next class you can try to answer why for a fillet weld we are taking Fu value, but for a groove weld we are taking Fy value. So for a fillet weld, the code requires you to take Fu divided by root 3, assuming that the failure is governed by shear only. But we know from experimental data that some of the fillet welds may have higher capacity, especially the end fillet may have a higher capacity, but the code requires you to assume it to be Fu by root 3. Okay, and then again LWTE. Now TE here for a fillet, as we had discussed, for a fillet the TE is given as this length. This is TE. Okay, so that TE will be taken multiplied by the length of the weld divided by gamma mw. So it's quite straightforward. There are no surprises here. Okay. Now we know how to calculate the strength. Then there are some considerations that you have to pay attention to when you design the fillet. So one thing is that the minimum size of the fillet weld, or minimum size of the um, yeah, for fillet weld. For a groove weld, you don't have to worry about the minimum size, because the groove weld, usually when it is full penetration weld, it has the same size as the plates that it is connecting. But for fillet welds, the size of the weld can be anything. So you are welding two plates together which are configured like this, and the fillet weld can be of any size, whatever you require. So let's say you require a weld of only 3 mm size from load points or from strength point of view, but there is the requirement as per the code that a minimum weld size is recommended for the plates that you are using. Okay, so this says minimum size of the first run. There is a table in the Indian code which provides you the list of minimum size of the first run or a single run fillet weld. So what it says is that basically if you have a multi-run weld, so let's say you need to do 3 runs, 3 passes of the, sorry. So I'm providing a fillet weld. Let's say I'm providing a fillet weld and I have to do, what happened? I'm providing a fillet weld and I am planning to do a 3-pass fillet weld like this. Okay. Now the code says that even though you are doing the 3 passes, the first pass should be at least of this size for the plate thickness size this. So for any plate thickness up to 10 mm, for any plate thickness up to 10 mm thickness, the first pass, or if it's a single weld, then the weld size should not be less than 3 mm. So even though maybe structurally I required only 2 mm size weld, but if the plate, no matter what size the plate is, up to 10 mm, the weld has to be at least 3 mm. So, or the first pass has to be at least 3 mm. At least it should be greater than 3 mm. Fine. If the plates are thicker than 10 mm and up to 20 mm, the weld should be at least 5 mm thick size. Okay. And the reason for specifying these values, various values, is because what you want your fillet weld to be able to fuse the base metal, right? And the challenge is that if you use too small, the weld that is too small in size, then it will not have enough heat, because basically what you are doing, you are depositing some molten metal on top of your plates, the base metal. And if the metal that you're depositing is not large enough in quantity, then it will basically lead to the solidifying or cooling down of the deposit very quickly, and will not effectively melt the base metal also. Basically what you want is where the deposit metal is where the filler material is deposited, there the base metal should also melt and fuse with the filler metal. But if you don't deposit enough amount of filler metal, then that won't happen. So therefore you are required to provide at least a minimum thickness of the um, weld for the first pass, or for the single pass weld. Okay. Additionally, for fillet welds, you are required to satisfy a few more requirements. So for example, we have this kind of a joint where this is the base plate, this is the base plate, or the bottom plate, and then another plate or another angle or something is welded on top of it. So this is the bottom plate and this is the top plate. This is the top plate, this is the bottom plate. These are two views of the same welded connection, and the two are welded together using fillet welds. So these are welded all around the plate. Now at the ends, the code requires that the effective thickness of the weld, that is this dimension, right, this diagonal dimension, that should be greater than or equal to the thickness of the top plate. So the thickness of the top plate is T. So this weld size, not the size, the weld effective thickness should not be less than 0.5 times the thickness of the plate. All right. So maybe on the sides you may have a smaller weld, but towards the end, the weld should be at least this big. So at the end, you have to have at least this big a weld. And if this weld is bigger and if it is equal sized, that means its projection on the horizontal surface will be larger here. Whereas this weld can be of a smaller size. That depends on your load requirement. So let's say the load is not very high and you require a smaller size weld everywhere. So here the weld is smaller, but near the ends the weld is larger. And then what the code also says is that you have to do a gradual transition from this small size weld to the larger size weld. It should not happen that you come with a small size weld all the way up to here and then suddenly increase the weld size at this edge. You have to do a gradual transition from the small size weld to the larger size weld. Okay, so both things are to be considered. All of these things are being taken from IS 800. In addition to these, whenever you have any, it may be a side fillet or it may be an end fillet, irrespective of that, you need to have at least certain part of the top plate exposed. Okay, so if the top plate is made of an element which is hot rolled, so if it's a hot roll, it will most likely have a curved surface like this. It will have a toe. So if it has a toe of a rolled section, then you need to have the exposed part, which is not hidden inside the weld, should be at least quarter of the total thickness of this top plate. At least one fourth of the T should be exposed, should not be hidden inside the fillet weld. Also, if it's a square edge, then at least 1.5 millimeters should be free, should not be fused with the fillet weld. Okay, these two things have to be met. So now the previous requirement was that the weld should be at least of this size or bigger. Here it is saying the weld should be at this size or smaller, so that at least this much part is exposed, and you have to meet those requirements properly. Okay. Okay, so I think it's already 10:50 almost. So I have a few examples. Maybe I can do this example today, and in the next class I'll do another two examples, and maybe the last class of this, because we have to complete this syllabus or complete this course by this week, right? Next week is for I think for exams or something, so we cannot have classes in the next week. So I have two more lectures to go after today's class. So I'll talk about some other types of connections, some more generic details about connections in the last class. Tomorrow's class I'll do a couple of examples, but this example I want to complete today. So let's see how to do a groove weld or a butt joint using welded connections. So I have two plates to weld. One is of thickness T1, another one is thickness T2. Their thicknesses are given as 16 mm and 14 mm respectively. Both of them are made of Fe410 steel. So we know the yield strength of this steel, that is 250 MPa. The weld is not specified, so you can assume the 40 weld, right? So you remember the weld type is not given. So I'm assuming this EX40XX, the first one. So for that EX40XX, the ultimate stress is 410 and the yield stress is 330. Okay. Please remember that the yield stress of the electrode is 330 MPa and the yield strength of the base metal is 250 MPa for 410. So between the two, 250 and 331, 250 is smaller, so I can use 250 MPa. Okay. So it's a full penetration weld. So my TE is equal to T1, that is equal to 14 mm. So TE is 14 mm. Okay. LW is the length. LW is given as okay, 175. Length of the weld is 175 mm, so I can take 175 mm. Fy, that will be less smaller of the 250 and 331, so I'll take 250 here, and the factor of safety divided by factor of safety, that is gamma mw. So it is a shop welded weld, so therefore the gamma mw is equal to 1.29, 1.25. That comes out to be 490 kilonewton. Okay, and the factored load that was acting on this weld was 430 kilonewton. So it turns out that the design capacity of this weld is 490, which is greater than the demand 430. So it is a safe welded connection. Okay, any questions? Anybody? Okay, so if you don't have any any questions, I think we can um, call it a day, and we'll continue day after tomorrow, Wednesday. I have two more examples to discuss, and then after that, I'll talk a little bit about actually more practical type of connections. All right. All right. Thank you.